Well, thank you very much, everybody, and thank you for your attention and for the invitation and the opportunity to share a little bit of a different perspective. I noticed that this session it has included many geneticists, and throughout the meeting there has been a component of genetics, and this talk is going to go back to basics to a certain extent, and is the concept of how do we deal with the results of genetic testing, and what is it that we want to obtain when we order genetic testing, and the big conundrum, which is the issue of variants of uncertain significance. So I do work as a consultant for pharmaceutical companies related to my other aspect, which is more for skeletal disorders. But in the context of today's presentation, I do not include any of that work. By the end of this presentation, I hope that you understand the role of genetics in rare forms of EDS. And as Dr. Byers mentioned, I think that the role and the use is still something that we are debating. It does link to the subsequent talk about availability of genetic testing, and the application of genetic technologies may not be the same in different countries. We're going to describe the methodologies that are available for testing that range from a single variant testing when you have identified a particular residue change in a family, to all the way to genome sequencing, which now comes in a variety of forms, both as short-read genomes and long-read genomes. We're going to describe the types of possible results for genetic testing, including benign, likely pathogenic, and the big gap in between, VUS, and hopefully develop a framework for the understanding of these variants. So a brief tour through the connective tissue is necessary in order for us to understand the genes that we're testing. By definition, the connective tissue is that connects and supports or separates tissues. We don't often think about it as much. However, when it fails, it is very obvious that there is a problem, and it has important functions in regulating the signaling molecules that we have heard in many other talks. Typically, it has relatively few cells that are embedded in an amorphous matrix that has collagen fibers, and some people equate connective tissue disorders with collagenopathies, but that's not always the case, because collagen is not the only player. There's many other structural components in that extracellular matrix that may lead to similar features, and they come from cartilaginous, fatty, and elastic tissues. So if we look at it from pathophysiology of Ehlers-Danlos, the function of those extracellular matrix fibrils include directing the formation of the elastic fibers, linking those elastic fibers to each other and to other components of the extracellular matrix, such as the vessels, the nerve endings, and the tissues underlying, and anchoring the cells in position, providing the elasticity that is needed. In terms of the composition, one of the big players that we have heard about today include the fibrillar collagens, which are exemplified there and that Dr. Byers talked about, that have a very specific structural arrangement that means that not all variation would lead to the same effect. We have elastic fibers, we have microfibrils with at least 8 proteins being part of those, and we have glycosaminoglycans, which are sulfated proteins. And when I talk to our trainees and to our patients about sulfur, when we are in biochemistry, we talk about disulfide bonds being important, and they're very important in allowing a protein to fold and to bend, yet go back to the position in which it should be. And if we have a problem with the sulfation of those bonds, with the creation of those bonds, the tissue may be excessively elastic or may have a problem going back to the shape that it was before. In terms of the collagens that are involved in the extracellular matrix, we have, and we have heard today talk about 3 specifically. We have collagen type 1, which is expressed principally in bone. And so When you talk to a geneticist about variation in collagen type 1, we tend to think first of bone fragility and osteogenesis imperfecta. However, as we know, they can also, they're also expressed in tendons, they're also expressed to a certain extent in skin, and may lead to the characteristic features of some of the forms of Ehlers-Danlos. Then we have collagen type 3 that is expressed in the vascular system and in hollow organs, and as we heard, is very critical in lung, is critical. So even though the name is vascular, it is a component of many other elements of the body, and collagen type 5, which is expressed in the extracellular matrix in the cornea. There are proteins that modify or interact with those extracellular collagens. So we have lysine hydroxylase, plot1, that adds a very necessary modification to a lysine residue on a collagen fibril. And as you see from the name, now we don't have a structural component, but we have an enzyme that modifies that structural component. And the importance of that is that enzymes in general, if you have half of the amount, you tend to do okay. And those tend to be recessive in nature. You need to have both copies affected. And that's relevant in the interpretation of variants. Then you have ADAMTS2 gene that codes for the procollagen 1 N proteinase, important for the maturation of collagen. We have tenascin XB gene that is secreted by matrix cells and is related to the formation of the elastic fiber network. And one thing to remember about tenascin X is that unfortunately it has a pseudogene that was left in our genome in the process of evolution, and that pseudogene can lead to abnormal results being picked up by certain sequencing technologies that may not correspond to the actual gene that is coding for the protein. So that's another consideration. Here we have a long list, and I'm not going to go through each one of them, but I do want to point out that, Here we have latent transforming growth factor beta binding proteins, TGF-beta. The role of TGF-beta has been discussed more in another connective tissue disorder, Marfan syndrome, and it is presumed a dysregulation of TGF-beta signaling is presumed to be part of the pathophysiology of some of the features, including the pulmonary features. The issue is that these proteins are present in the extracellular matrix, and they play that regulatory role. And so we may not be only dealing with structural changes per se of the proteins, but of their capacity to regulate the expression of other genes. So we're dealing with the genetically defined forms of Ehlers-Danlos, or the rare types, or the rarer types, and hopefully at some point we will understand the genetics or the mechanisms that lead to the hypermobile type of EDS. I have separated them into two buckets because it's the rare and then the ultra rare. We have heard today experiences from individuals with classical EDS, autosomal dominant, meaning one copy is enough to lead to the variation. And we have collagen type 5 in its two genes that code for collagen type 5 as being associated with the majority of cases. Then we have the classical-like tenascin XB. We have the vascular type with collagen 3. And then we have the ultra-rare types that are associated with variations in other genes that we have already heard today and through the previous days. So a patient comes, and I generally, as a geneticist, and I think that a lot of clinics in genetics, we're trying to answer 4 questions. Is the problem that you have genetic in nature or not? And by genetic, we're not meaning hereditary necessarily, because there is the possibility that there was a new mutation or a new variation that happened in the egg or the sperm that gave rise to that child. Second question, is there a test that can identify that variation? And we're going to have to select from this menu of tests what the best approach is. Third, we're going to try to give you an idea of prognosis, best treatment, best management, and finally, what is the risk of it happening again from a family perspective. So single gene analysis, traditionally done by Sanger sequencing, although even now as next generation sequencing becomes more and more prevalent, even single gene can be done in the context of next generation. You can even test one particular mutation. You can create primers and test for that mutation. You can create primers and amplify just the areas of that gene. And that is if you have a very good candidate. You think you know what it is, you test that. You can do a gene panel that includes several genes that are associated with the particular disorder, but not all genes that code for proteins relevant to the body. Then you have an exome that reads all the coding parts of the genetic material that codes for proteins. And in an exome, we're really interpreting the maximum 6,000 genes that we know associated with disease. We're not interpreting the 22,000 genes that are actually read. And when we look at proportion, we're reading a very small percentage of the genetic information. Yes, it's critical because it leads to the coding of protein, but we're missing out on the regulatory regions that are a critical part, or so we also think. And so we have finally the genome, which reads both coding sequences, regulatory sequencings, and everything in between. Once you decide which one you're going to go, and the advantages are highlighted here, as you increase the amount of data, you increase the possibility of finding, to a certain extent, variation that you will not be able to interpret. The reason why there's a caveat is because the pre-test probability also changes, and sometimes the probability of finding a variant of uncertain significance may be higher in a gene panel than in a genome, just because when you order a gene panel, you're telling the lab that you think the patient has that condition. So they will more likely to report any variation, even if it doesn't meet the whole spectrum of criteria. In terms of panels, so we have at the Hospital for Sick Children, where I work, we have a panel that includes at present 17 genes. Clearly, it needs updating with all the genes that have been published, but there has been some delay in the discussion as to which genes are most relevant to add to the panel. Then there are labs that have a different approach, and instead of including all possible causative genes, they do a dominant panel. So if the pattern of inheritance is dominant, or it's presumed to be dominant, you just limit your search to these, and they have a recessive panel or a combination. At the end, this is what you can get. You can either find no pathogenic variants. We're not twins of one another, so there's always going to be variation. However, that variation may be part of the normal variation, and how we determine whether it's part of the normal variation is frequency in the population. Caveat, if your patient is from a population that is underrepresented in the control databases, it may be rare, but it may be rare because that particular ethnic background is rare. So you always need to be careful about that correction. In general, if it's non-pathogenic, you're talking about a patient that falls under the normal variation. Likely not pathogenic also within the population, however, not as frequent and as these. But then we have a very, very big percentage from the probability of 5% to 94%, that is, we don't know. VUS just means we don't have enough evidence at this moment to tell you whether your variation is relevant or not. There is a lot of discussion in labs around the world. I've heard more of the discussion in the US and in Europe to parcel out this particular area into at least a number so that you know, I don't know, but I think it's most likely pathogenic versus I don't know, but I think it's leaning towards benign. And that's where geneticists play a major role. We go, we see, we looked at the databases, we see at the patient, does it fit with the presentation? Is this seen in other organisms does it make sense versus these two categories in which you are able to make the diagnosis. I think that the reason for this talk, and one of the messages today was, unfortunately at this moment, the consensus is we should not make clinical decisions based on variants of uncertain significance. Variants of uncertain significance do not constitute a diagnosis. However, variants of uncertain significance would warrant a discussion with a geneticist for further interpretation. I often contact my expert colleagues around the world, ask them if they have seen the variant. We recently interacted with Peter about both variants in collagen type 1 and in collagen type 3, because I saw a family that had a variant of uncertain significance that, according to the lab, was cold, which is one of the ways that you put it on the low end. But when you look at the residue, it affected one of those conserved glycines. And thankfully, Peter has experience and had seen a patient that had that variant. And based on the functional analysis, it is unlikely to be associated with disease. But yes, VUSs can still be associated with disease, and they can still be the explanation for your patient. It's just we should not make definite clinical decisions based on them. In conclusion, I think that we all agree that the Ehlers-Danlos are heterogeneous, and they have varying degrees of the typical characteristics of joint hypermobility and connective tissue hyperextensibility. The diagnosis remains primarily clinical criteria. However, more and more with the availability of genetic testing, we're seeing that as a concurrent or even first step in some centers. The classical, the vascular, and the rare forms of EDS can be confirmed with molecular testing. The hypermobile type at present, no. And in our center, we are not offering genetic testing for patients that only meet criteria for the hypermobile type, unless they have some element of overlap with the others. And the molecular, because of the molecular basis being unknown, and the interpretation of the molecular testing needs to take into account the clinical presentation of the patient, as well as the evidence for pathogenicity of the particular variant, and may take more than one visit to the geneticist. Some of the VUSs, we tell the patient, you need to contact us in a year or two. We're going to reinterpret. Depending on the potential complications, if it's a vascular patient, we will monitor, we will do the recommendations of watching, but we will not give them the diagnosis. A mantra that I tell my trainees is, no diagnosis is better than the wrong diagnosis, because once you give it, the patient is probably going to carry it for life, and the medical record perpetuates it. And then it does have consequences. We have seen patients that were given the wrong diagnosis that come later on, and we're like, no, you actually don't have confirmation of the diagnosis. Thank you very much, and I'm happy to discuss further during the panel at the end. Thank you.